Okay, welcome back. So in our previous video, we looked at how we can find the inverse of a matrix using cofactor method. Now in this video, we're going to see how we can apply that method to finding a system of equations. So before that, let us look at some of the properties of square matrices. One of the properties is called the adjoint matrix property. What this property tells us is that the product of a square matrix A by its adjoint matrix is equal to the determinant of a matrix A times the identity matrix. This is part of the example that we looked at that I told you to go and solve it. So you should be able to show that when you multiply the matrix by its determinant, by its adjoint, then you should be able to get the determinant of that matrix times the identity matrix. The other property, which is very important, is called the inverse property. It says that if A and B are two square matrices of the same order, such that A times B is equal to B times A is equal to identity, then the matrix B is the inverse of matrix A, and matrix A is the inverse of matrix B. So if we let B is equal to A inverse, then we know that A times A inverse is equal to A inverse times A, and this is identity. This property is very useful because we can apply it in the following way. In part C says that if A and B are two matrices and A times X is equal to B, then X is equal to A inverse times B. We can demonstrate this in this way. So if we have A times X is equal to matrix B, then using this property here, it means I can multiply on the left-hand side by the inverse. So A inverse times matrix A times X is equal to, I need to multiply by the inverse on both sides. Sorry, not B inverse, but A inverse. So if I multiply by A inverse, so A inverse times B, and I know that this is going to be identity. So this is identity times X is equal to A inverse times B, and this simply X is equal to A inverse times B. And we're going to see shortly how we can apply this property. Okay, let us see how we can apply this one. Let us look at this example. It says that given that A is equal to that, determine the inverse of matrix A. I know by now everyone is able to determine the inverse. Let's do it together. The first thing is to find the determinant. So we can easily find the determinant of matrix A. So the determinant of matrix A, we're going to have, if we multiply A, the minor of A is going to be, so we're going to have 1, minor of A is 1, 1, 1, negative 2. So if we multiply directly, we're going to have 1 times negative 2 is negative 2. Sorry about that. We're going to have negative 2. Then minus 1 times 1 is 1. So we go to 2. 2 is negative. So let us look at the minor of 2. So the minor of 2 is simply 2, 1, 3, negative 2. So if you multiply 2 times negative 2 is negative 4. Minus 3 times 1 is 3, so it's negative 7. So here, what we're going to have is, we're going to have 2 times 2 is negative 4 minus 3. Okay. Then plus 3. So the minor of 3 is 2, 1, 3, 1. So 1 times 2 is 2 minus 3 times 1 is 3. So if we simplify this, we're going to get, this is negative 3. Then this is negative 7 times negative 2, which is 14. Then this is 2 minus 3 is negative 1 times 3 is negative 3. And this gives us 8. So you can see that the determinant is equal to 8. So to find the matrix of the adjoint, let us find the cofactor. So let me use this space. So let us find the cofactor. So you can go straight. By now you know how to find the cofactor. If you're not sure, please check the previous video. Let us find the cofactor of matrix. So we're going to call this C. So we'll go directly. So we know the minor of element 1 is 1, 2, 1, 1, 1, negative 2. So its determinant is 1 times negative 2 is negative 2, minus 1 times 1 is 1. So this gives us negative 2 minus 1, which is negative 3. It gives us negative 3 as our cofactor there. Okay. Then the minor of 2 is simply 2, 1, 3, negative 2. So we're going to have 2 times negative 2 is negative 4, minus 3 times 1 is 3. So negative 4 minus 3 is negative 7. But remember, this third element is negative, so it becomes positive 7. Okay. The minor of 3 is 2, 1, 3, 1. So we have 2 times 1, which is 2, minus 3 times 1, which is 3. So 2 minus 3 is negative 1. So we have negative 1 here. Let us go into the second row. So the minor of 2 is simply 2, 3, 1, negative 2. So 2 times negative 2 is negative 4, minus 1 times 3 is 3. So negative 4 minus 3 is negative 7. So here negative times negative in the third one, second row is negative. So it becomes positive 7. Okay. Second element in row number 2, we have, what is the minor? The minor is simply 1, 3, then 3, negative 2. So 1 times negative 2 is negative 2, minus 3 times 3 is 9, so negative 2 minus 3, this gives us negative 11. Then the minor of 1, we have the minor of 1, we have 1, 2, and 3, 1. So 1 times 1 is 1, minus 3 times 2 is 6. So 1 times 6 is negative 5. But there, that one is, the sign is negative, so negative times negative becomes positive 5. So the last one, the last element in row number, no, the first element in row 3, the minor is simply 2, 3, 1, 1. So 2 times 1 is 2, minus 1 times 3 is 3. So 2 minus 1 is 3. And the sign there is positive. So we have negative 1 there. The second element in row 3, its minor is simply 1, 3, 2, 1. So determinant is 1 times 1 is 1, 2 times 3 is 6, so 1 minus 6 is negative 5. And there we get the sign there is negative, so negative times negative becomes positive. Okay. Then the last element in row number 3 is the minor is 1, 2, 2, 1. So the determinant is 1 times 1 is 1, minus 2 times 2 is negative 4. It's 4. So you have 1 minus 4 is negative 3. So there we're going to have negative 3 because this sign there is positive. So this is our matrix of cofactors. And we know the adjoint of matrix A, which is equal to the transpose of matrix of cofactors. So if we transpose the above matrix, we're going to have -3, 7, -1, 7, -11, 5, then -1, 5, then -3. So this is our adjoint matrix. And therefore, now that we have adjoint matrix, then using the formula, A inverse is equal to 1 over determinant of matrix A times the adjoint of matrix A. This is simply determinant is 8, so we're going to have 1 over 8 times -3, then 7, -1, then 7, -11, then 5, -1, then 5, then -3. So this is our inverse of matrix A. Now let us go to the most interesting part. Part B says, hence or otherwise, solve the following system. So the given system is that one. Now, interestingly, let us see if we can write the matrix of coefficient, or we can write this system in matrix form. Let us write this system in matrix form. So part B, let us see. So we can write this matrix as 1. So the coefficients of x is 1, for y is 2, for z is 3, for x is 2, for y is 1, for z is 1, for x is 3, for y is 1, for z is -2. So we can now write this is x, this is y, and this is z. So this is how we can write this matrix, this system in matrix form. This is equal to 6, this is 5, this is 1. Okay. So interestingly, so this is how we can represent that system in matrix form. Now, something interesting is you can see that this is the matrix A. Okay. And we can call this matrix as matrix X, and this is matrix B. So this forms something like A X is equal to matrix B. And since we want to solve this system, we want to find the values for x, y, and z, and we can use that property that we discussed above, where we can multiply the left-hand side both by A inverse times A times X, and also A inverse times B. And we know this gives us an identity matrix. So this becomes IX is equal to A inverse B. And this one is simply X is equal to A inverse B. Why? Because an identity matrix is the same, similar to 1. And 1 times anything is the same answer. So we know that for us to solve this system above, we just need to multiply the A inverse there by matrix B. And this is our matrix B, and A inverse is the one we have found above there. Okay? So in other words, let's see how this works out. So what we're going to do is, so we're going to have A inverse. A inverse is simply 1 over 8 times -3, 7, -1, 7, -11, 5, then -1, 5, then -3, and then you need to multiply by matrix B, which is simply the matrix of solutions. So we have 6, then you have 5, then you have 1. Okay, so we can easily do this one. So we all know how to multiply this. So rows by columns. So we're going to have 3 times -6. So this gives us -18, -18 plus, then 7 times 5, it gives us 35, 35, then plus, then 1 times 1 is, sorry, -1 times 1, this is -1. Okay. I will multiply 1 over 8 at the end. So let me put it like this. This is multiplied by 1 over 8. Okay. Let's go to the second row. So we have 7 times 6, which is 42. Then we have 11 times 5, negative 11 times 5, it gives us negative 55. Then we have 5 times 1, it gives us positive 5. The last row, we have 1 times 6 is negative 1 times 6 is negative 6. Then you have 5 times 5 is positive 25. And negative 3 times 1 is negative 3. So what we get is, we now write properly 1 over 8. So let us sum this one. So if you're not sure, you can get your calculator. Then you multiply. So you're going to have negative 18 plus 35 plus negative 1, which is same as negative 1. So we get 16. Okay. The second one, we have 42 minus 55 plus 5. This gives us negative 8. Then the last one is negative 6 plus 25 minus 3. This gives us 60. So what you have there is, we see that, so we know that this is X, matrix X. So in other words, this is same as what we have remain with this is X, Y, and Z, which is equal to that. And so X, Y, and Z is equal to, so if we multiply through what is inside, so we're going to have 16 times 1 over 8. This gives us 2. Then 1 over 8 times negative 8, negative 1. 1 over 8 times 16 is 2. What does this mean? This means that X is equal to 2, Y is equal to negative 1, and Z is equal to 2. And this is how we solve a system of equations using the inverse method. Okay, thank you very much for listening. So this is how we can go about it.